Good afternoon, everyone. So let me start then. First of all, yes, thank you for the invitation. So I'm very interested in interpretability recently in reinforced learning. So it's a pleasure to share what we did recently. The only thing is I have to apologize in advance as we decided very recently to give this talk. So I didn't have the time to really polish my slides, and so I'm reusing some slides that we had for our internal discussion. So they are not as polished as I would like to those slides to be. So feel free to ask questions if I'm not clear. Also, yeah, here I'm in Asia right now, so it's the evening. So I've already worked 12 hours. So my mind is not as clear as it could be. So if I'm not clear, yeah.
You're a hero for reinforcement learning, in other words.
Okay. Okay. Anyway, thank you for the invitation. So let me move to the other screen. Okay. Okay. So first of all, I'm going to give a short introduction to our team. So I'm an associate professor at this joint institute, which is a partnership between University of Michigan and Shanghai Jiaotong University. So it's an institute that's part of Shanghai Jiaotong University, and so it's located in Shanghai in China. Okay, and so currently we have 5 PhD students, 1 master student. Several of my master students recently graduated, in fact. And for September, we will have some new graduate students who are going to join our team. So, so in general, we are interested in reinforced learning and deep reinforced learning. And here are some of the topics that are investigated in our team. So, of course, interpretability. So I will talk more about this. We are also interested in fairness, especially when you have reinforced learning agents interacting with many users. So we want to be fair to all the users. Another direction that we are interested in is how to exploit invariance or more generally equivariance in a given task to design more efficient algorithms for reinforced learning. And we also work on more classic problems in reinforced learning, like problems related to how to obtain the reward function. So if you have tried to apply reinforced learning to some problems, you know that designing the right reward function is very hard. And just one other direction that I'm really excited about is the application of reinforced learning to obtain heuristic solvers for combinatorial optimization problem, like traveling salesman person problem. Yeah, I think that's.
Sorry, I just have to jump in here because we had a seminar on this topic, and I invite everyone to watch the recording. Yeah, we were talking about using it for traveling salesmen. We had some people who were solving traveling salesmen with reinforcement learning come up, and it's very interesting work there.
Yeah. So then, is it a public recording?
Yes, it's on YouTube.
Okay, then I will check it. Then I'm also very interested in this application because I think it's a very nice application domain for reinforcement learning. Okay, and I just want to do a small advertisement. So if you are interested in studying or working in Shanghai, and so especially working on reinforced learning, so feel free to contact me. Okay, so let's move on to the meat of this talk. So let me start with some motivation for interpretable reinforced learning. Although I guess if you're attending this seminar, you are already convinced that it's an important topic. Deep reinforced learning has shown that it's a very powerful and generic method to solve sequential decision-making problems and control problems. But the issue comes from the fact that we are using deep learning or neural networks, and the policy we obtain is hard to understand. So it's a black box policy, and then that leads to other issues like generalizability and robustness. So I guess you have heard about issues like when applying deep reinforced learning to solve Miss Pac-Man, if you change one pixel, so that completely that will lead to learn policy to fail completely. So there's really a problem of brittleness in deep reinforced learning. And I think interpretable reinforced learning can solve all those related problems. And of course, if you want to apply reinforced learning in a high-stake domain like autonomous driving, of course, you want to have a policy that's interpretable, that you can understand, you can verify, and possibly debug if there are some issues. And so it was a new topic for us 2 years ago, and we started to work on this with a collaborative research project with Huawei NOAA's ARC Lab. So it was an exploratory project for them as well. And so the question they were interested in is if it was possible to learn efficiently an interpretable policy for autonomous driving. So here we are thinking about decision making, like should I so when should I change lane to take over a car, or if you arrive in an intersection, so should I give the way, or can I go through the intersection? So this kind of high-level decision making. And the approach they had in mind was to use neurosymbolic methods. And in particular, they were interested in first-order logic. And so that's the context of how we started this research direction. So here are the different collaborators who work on this project. So on our side, so before I had 2 postdocs, Pierre Glanois and Mathieu Zimmer, and several of my graduate students also participated in this work. And so we have done two main work in this project, and so that the effort was led by the 2 postdocs. Okay, and so after working about 1 year or 1.5 years on this topic, so here are our research outcomes. So as it was a new topic for us, we did a large survey of work that's related to interpretable reinforced learning, and we wrote a survey paper on this topic. So if you're interested, you can check that. And so currently it's under review. And so today I'm going to focus on a differentiable logic. So it's one of the models we developed. So that was done, and the effort was led by Mathieu Zimmer. And so it's also under review. Another work that we did that I won't talk much about it today is hierarchical rule induction. So this work was led by the other postdoc, Pierre Glanois. And so we are happy that he was accepted at HTML this year. And so if you're interested, you can check this paper. And the whole project was to try to apply this kind of technique in autonomous driving. So we have made some demos, and of course it's on a very simple simulator, but we have made this application, and so we can learn some interpretable policies in this context, and we hope to present this kind of work in a workshop this year. Okay, so I will focus on differentiable logic machines. And so here's the context. So we assume that we can describe the world with predicates. So we have a relational representation of the world. So in the reinforced learning, it means that we are describing the state or the observation with some predicates. So if you're not familiar with logic, so predicates you can think of them as just functions that take some objects and that will return true or false. And so that will describe properties of objects in the world and relations between objects in the world. And so this is the input of, so that would be the input of our policies. And so what we want to learn is a policy that's interpretable. And so in this context, it means that the policy will be just a first order logic program. So first order logic formula. So we could learn this kind of policy either via imitation learning or reinforced learning. But our goal was to try to obtain those kind of policies via reinforced learning. But we have tried both. A nice property of this kind of setting is that as we are learning a first order logic program, so this kind of model is independent of the number of objects and of course the number of actions in the world. And so that means that we could train on a small settings with a few number of objects, learn a first order logic formula, and then apply it in a context where there are many more number of objects. And so just to make it a bit more concrete, here is a very classic example of planning problem, which is a blocks world problem. So here you have a certain number of blocks in your world. They are in some configuration. And so you want to move the box and reach a target configuration. And so, of course, you can move one box at a time, and you can move a box only if there's no box on it. And you can move a box to another box if this other box has no box on it. And so here, this problem could be described like this. So you may have some initial predicates to describe the world, like on. So on x, y means that the x is on y, if this is true. And you can have also is ground x to say that one object corresponds to the ground. And of course, the ground cannot be moved. And you have a predicate here in this example, clear x, to say that there's no objects on x. And using those kind of initial predicates, we could learn more complex concepts like movable. So movable of x means that x could be moved. And it could be moved if x is not the ground and if it's clear. Okay, and we can also learn, for example, placeable. So if we can place a block on this object, and here we can do that if it's a ground or if it's clear. Okay, and so the goal is given some initial predicates. Here there will be only 3. We want to learn a predicate that corresponds to an action. So here the action is move x, y, that says that we want to move x over y. And this definition of move would be a first order logic formula that's constructed with the initial predicates. Okay, so that's what we want to achieve. Okay, so there were a lot of relative work. So people have worked on similar problems. In the context of supervised learning, what I describe is called inductive logic programming. And so in ILP, so basically the problem is to learn a first order logic classifier given some positive and negative examples described with some initial predicates. Okay, and so there's a long tradition on this problem, and so many methods have been proposed. The traditional method consists in searching directly in the discrete space of a logic program and try to find this classifier. So as you may guess, it doesn't scale very well because this space of program, so it's discrete and the size of this space increases exponentially fast with the depth of the program. Yeah, and another issue with this kind of traditional method is that it's not very robust to noise. So if you have a data set that's noisy, so some of the examples are mislabeled, then those methods will not work very well. More recently, there were some differentiable methods that were proposed. So I'll mention just 2 of them, but there are many others. So there is a DILP and NLM. So DILP is inspired, in fact, by the traditional methods. So it's going to try to search in this space of program, but by relaxing this discrete space into a continuous space. And so the way it does this is it assumes that you have some templates, so the kind of rules that you can use to build a program, and it will define weights to trainable weights to select the templates that should be used to build the program. Okay, so this is the approach for DILP. And for NLM, it's basically a deep learning method with a strong architectural bias to enforce some kind of logical structure. And so the nice thing with this kind of method is that it's robust to noise, like any differentiable method. And as it's also differentiable, we can, of course, also train it with reinforced learning. And so that's the property we were interested in. And to summarize, so most of the methods proposed for ILP, in fact, don't scale very well. The differentiable one scale a bit better, and the one that scale the best is NLM. But the issue with NLM is like it's as a deep learning method, it's not interpretable, while the other methods can provide interpretable solution.
Wait, can you expand on that a little bit? Because the output of that deep learning architecture is a logic, right? And that logic is a set of predicates that we can interpret.
Yeah. So I'm going to explain this architecture, in fact, because our work is based on NLM. It is inspired by this architecture, and our work was to make this kind of idea interpretable. Okay, so I will explain why it's not so interpretable.
Great.
Okay, so this is our approach. So it's inspired by NLM. So the architecture proposed by NLM has this kind of structure. It's a hierarchical model. You have modules, different layers, and they are connected in some ways. And so each module, so you have different layers, and also each module will be also will correspond to some arity for the predicates. So the arity of a predicate corresponds to the number of arguments the predicate can take. So nullary predicates are just Boolean variables. You have unary predicates that correspond to predicates that can be evaluated on one object. Binary predicates needs two objects, and so on. Okay, and each module, each box that you have here will correspond to predicates of a certain arity that are available at a given depth. Okay, and the first layer, so it's the input. And so in my example here, we have only binary predicates, but you could imagine that you could have unary predicates as well, and so on. And so the nice idea in NLM is that each box will create. So in language of ILP, it's called invent. You will invent predicates of a certain arity. So this box will. The task of this box is to invent the binary predicates using predicates of the previous layer. Okay, and so each box will create a new predicates based on predicates that were invented or were available in the previous layer. And the nice idea of NLM is that the predicates that will be built based on predicates of the same arity. And so this, let's take this example, that this box will create binary predicates from binary predicates that we can obtain from the previous layer. So we have the binary predicates of the previous layer, but we can also make some transformation binary. So those are the fixed operations that I mentioned here. So you can, for example, from ternary predicate, you can turn them into binary predicates by using a for all or exist on one of the variable, and so that will remove one of the arguments, and so that will create a binary predicate. And the same way, if you have in an unary predicate, you could add a variable to this unary predicate. So of course, this extra variable that you add doesn't have any impact on the evaluation of the predicate, but I will make this unary predicate as a binary predicate. Okay, so you can apply those kind of operations everywhere, and so that the input of one box will be predicates of the arity of that box. Okay, so you have this architecture, and of course, at the end, you have the predicates that you want to learn. So in the example of blocks world, we want to learn move x, y. Okay, and so basically this architecture try to enforce this kind of logic program that we want to learn. So in NLM, the way they implemented each box is a shallow MLP. And so that's why I say it's not very interpretable, because you have many weights in all the boxes that correspond to layers of an MLP.
Okay, so in the end, you basically get a formula that contains all possible permutations of operators, just with different weights, right?
So the weights of an LP will correspond to computing a logic formula, but the only thing is that we do it as a weighted sum, plus potentially some non-linearity. And so if you have many weights like this, many multi-layer perceptron, it's very hard to interpret those weights as a logic formula.
What about the fact that you start with only binary predicates? Is it some fundamental constraint, or is it just something that you decided?
This is what I said. Is just for this example, we have only binary predicates, and that corresponds to one of the tasks we are going to try to solve, which is the blocks world problem. But
in general, it's not
with any number of predicates and with different RITs, there's no problem. Okay, so the architecture is very general. So you can have different boxes for the initial predicates, and you could also learn several target predicates as well.
So may I also ask a short question?
Yeah, sure, go ahead.
Yes, could you be more specific about the optimization task you're solving here during learning? So what kind of optimization tasks you're having here while learning these formulas?
Yeah, okay, that's my next slide.
Okay, sorry.
I will explain how we can train this kind of model. So here I just want to explain the architecture of the model. And so what I just explained is the architecture that was proposed in NLM. And the other operation I didn't explain yet is we can also apply permutation over the order of the arguments of a predicate. So that will so that means we can build a formula where the argument is swapped, and so that leads to more expressive formulas. Okay, and so here, just as an example, here, if you are learning move x, y, and it has this form, it means that move x, y, so this what's in parentheses will be, for example, invented in the previous box. And here we can see that maybe it's a conjunction of 3 terms. And so the binary terms maybe are obtained in this box, and the last term top x could be obtained from this box. And using expansion, we add a extra y in this predicate to make it binary, and so the whole thing can be learned here. Okay, and so the predicates come from the previous boxes. Okay, so hopefully I was clear enough. So the issue with NLM is that at the end you learn some weights there, but it's hard to interpret them as a final logic formula or logic program when you have your trained model. So our idea is very simple: is to replace all the boxes by this kind of term. So assuming that we only take we build the formula only with 2 terms. So here is the example with the end. So, sorry, it's my next slide where I explain how we train the model. So I will explain that. So here I just want to finish explaining the architecture of DLM, our method. So we replace the shallow multi-layer perceptron by something like this. And so here the idea is that we are going to maybe invent a predicate PLB, so at some layer L for given RIT. And so we take all the predicates of the same RT that we have built in the previous layer. And what we want is to create this new predicate as a conjunction. And so, so what we want is to learn to select one predicate P and another predicate P prime. And so the weights WP are going and WP prime are going to be learned. And so they are just weights in 0, 1, and they have to sum to 1. Okay, and so this is example with AND. So the AND logic AND can be done with a product, and you could do you have a similar formula for the OR. And we have in fact also the negation to have more expressivity. So I will skip those kind of details. Okay, and so the weights WP, you can see that in fact it's like a softmax. So it could be expressed as a softmax. The only thing we did here is to add, we are going to add some noise in the softmaxes. So that's why we use what is called a Gumbel softmax. So for one weights WP, it's like a softmax. So the theta P correspond to trainable weights, and the GP corresponds to some noise that we inject at every iteration to so I will explain why we inject the noise. Okay, but the idea is very simple. So all the modules now will have is built with this kind of structure. Okay, now I can explain how it's trained. So if you train in a supervised learning setting, so usually we use simply the cross entropy loss. As we are trying to learn an interpretable solution, so we want to have a first order logic formula. It's I mean, if you don't do anything special and we minimize this cross entropy loss, there's no guarantee that we are going to converge to a good first order logic formula. And so we may also converge to some solutions that are not interpretable. For example, when the WP are all different to 0, and so we may do some combinations of predicates. So what we want to obtain is, as we train, we want to select one of the P. So one of the WP should be very close to 1, and the other one should be close to 0. And so this is not so easy to achieve. And in fact, if you look at this the landscape of this loss, there are a lot of local minima. And so what we so our idea is to try to smooth this landscape. And so to smooth this landscape, we add those noise. So the Gumbel noise helps smooth the loss function that we are optimizing. And also we use a dropout to ensure that the weights we learn are kind of independent. And so that also helps conversion to a interpretable solution. Okay, and so the idea is relatively simple. So we try to minimize this cross entropy loss, and at the beginning we start with a large noise, and we reduce the noise, the dropout, and also the softmax temperature to try to converge to one interpretable solution. Okay, and the cross entropy loss can be computed. So here we are in the supervised setting in the usual way. So the only thing here is that you have to compute it for all evaluation of the target predicate. So that means for all this target predicate should be evaluated over all pairs of objects. So in this in the example where you want to learn the binary predicate, so the predicate has to be basically evaluated on all the objects, and then you can compute the cross entropy loss. So this is for supervised training. So as I said, as we have a differentiable model, we can also train it with in a reinforced learning setting. So the previous work, they use reinforce, and as you probably know, reinforce is a very inefficient algorithm. And so our idea was also to have a more, to use a more efficient reinforcement learning algorithm. So we wanted to use PPO. And to be able to use PPO, we had to design a critique, so to create an architecture for the critique. And so this is not so obvious because the architecture I just described is independent of the number of objects. Okay, so the number of weights that we have in this architecture is independent of the number of objects and actions. And so we need to have the same property for the architecture of the critique. So the reason is that when we are going to train, we are going to train on instances where the number of objects can change. And when we are going to apply our method, we are going to apply it on instances where the number of objects can also change. So that this is property that we need to have. So I don't know if you have the time to enter into the details, maybe quickly. So here are the initial predicates. So in this example, we have nullary predicates, unary predicates, and binary predicates. And so to make this architecture independent of the number of objects, we have a recurrent neural network. And so basically, we use several GRU units that are going to read all the input, different slices of the input. And so one thing I should have said is that all the predicates that we have can be represented as tensors. So if you have unary predicates, so if you have m objects, you can list the evaluation of the one predicate as a column vector, and here on the width would be the number of unary predicates we have. Okay, and binary predicates would be a tensor with a higher dimension. And so the GRU will read all the slices, and the interpretation is that the GRU will more or less summarize for each object what are the other objects it's related to. And so if you do it like this, so this architecture is basically independent of the number of objects. So the number of parameters we have in this architecture is independent of the number of objects. Okay, so the idea is to reduce everything into a tensor of this form, where we have so the information for all the objects, and we can aggregate everything at the end and give that to MLP to predict the value of a state. So if this describes a state. Okay, so that's the basic idea of the critique. And so once we have the critique, we can just apply PPO and everything works fine. But the only thing is that, of course, the kind of problem we try to solve is very hard because we want to learn a program with reinforced learning. And so, of course, if the initial task we want to solve is very hard, just training directly with PPO will not work. And so we also use the curriculum learning for harder problems. And even with curriculum learning, in fact, some tasks are not solvable with this kind of approach. So we propose also a simple idea called incremental training. So it's very simple. So you train the model either by supervised learning or via reinforced learning. You can extract the interpretable solution. Then you can look at the performance. If it's satisfying, then you can stop. You have find your interpretable solution. If it's not, even though the performance is not good enough, the interpretable solution solves the problem partially. And so in this logic program, maybe there are some invented predicates that are useful. And so what we do is we take all those invented predicates and we add them to the initial ones, and we retrain from zero. And we can repeat that several times. And in fact, that technique can help a lot. So here are the experimental results. So we evaluated our method on supervised learning and reinforced learning. So in supervised learning, that correspond to the ILP task that I mentioned before. And so there are some very classic tasks. Here is an example where we want to learn the concept of his grandparent, given a simpler concept like his son, his father, his daughter, his mother. And this is, for example, one logic program that we can learn. Okay, and so here I just want to show that, once we have learned our model and we have extracted a logic program, so our method scale very well. So compared to NLM, for example, we can, both in terms of computation time or memory consumption, we can deal with much larger problems. So on the x-axis, you have increasing number of objects in the instance. And so here it's for 2 different tasks. And so for all those tasks, we can scale better. So so this is for testing. Here the experimental result in a reinforced learning setting. So we try on different tasks. So it's more or less ordered in increasing level of difficulty. So the first 3 are simple problems in block swarm. So we also tried on algorithmic tasks like sorting. So we have a list of values and we want to sort them, or problems like in computational on graphs. So where we want to find the path between 2 nodes. And there is also one version of block swarm that's the most complicated one that we tried as well, and it was formulated in the NLM paper. And so NLRL corresponds to DILP, in fact. So this is extension of DILP in the reinforced learning setting. So we have NLM, and we try different versions of our method. So the first one is when we don't try to enforce interpretability. So we don't try to make the our weights converge to 0 and 1. And so in that case, our model works very well, and it's comparable with NLM. So in terms of success rates, so how many times given an instance we are able to solve it. We can also measure the performance in terms of average rewards. And so this is more classic performance metric for reinforced learning. So what's interesting here is that if we measure in terms of average reward, our model works better than NLM. And I think the reason maybe is that our architectural bias is stronger than the one used in NLM. And so the model we learn, even though it's not interpretable, can generalize better. And there is DLM, which corresponds to the interpretable version that I described. So here you can see that we solve everything well up to some level of difficulty. And so pass and backward are too hard. And the last one corresponds to, so DLM trained with this incremental training that I mentioned. So, and so here it's incremental training with supervised learning, so with the imitation learning. So we assume that we have a solution, or that, for example, that could have been learned using this non-interpretable method. And we try to copy it with interpretable policy. So if you do use this kind of training method, we can again solve everything with a 100% success rate.
In this incremental training, where do the new invented predicates come from? Do you have an algorithm for inducing them, or do you manually add them, or?
Yeah, so maybe I went too fast. So the idea is we train many times our model. So the first time we train it with input, so the input will be just the initial predicates we have to describe our observation. And so we can train it with the method, with reinforced learning, or with supervised learning. In fact, what I showed you is with supervised learning, because in fact, of course, solving a problem with supervised learning is simpler. So after training, we obtain a trained model, and we can extract a interpretable solution. So we extract a logic program, and we can evaluate that logic program, and we can measure its performance. And so usually if the problem is very, very hard, so the first training will not be sufficient. And so what we do is we take this interpretable solution that we have found. So it's a logic formula, and so inside this logic formula we have many invented predicates. And so we take all those invented predicates and we add them to the initial ones we have. And so now, for the next iteration of this incremental training method, the number of initial predicates will be larger. Okay, and we use the invented predicates we have obtained in the previous step.
Yeah, thanks.
And we train from zero again. And usually if the problem is hard, in fact, it's not sufficient. So we are going to extract again interpretable policy. And we are going to again extract invented predicates from it. And we are going to augment again the initial predicates. And we do that many times. And among the invented predicates, there are probably some that are useful, in fact, to solve the problem. And that can help learn a good solution later on. And so this is basically what we observe here. With this kind of incremental training, we can solve those harder tasks. And again, you can see that, so in terms of success rates, of course, it's comparable with the NLM. But then if you look in more details in terms of average rewards, so in terms of rewards, we get better rewards than NLM. So here for pass, probably this is the maximum, so we cannot really improve on that. Okay, so this is basically what we did for our first work in interpretable reinforced learning. So what I show you is one method that can learn interpretable policy, so as a first order logic program. We can do that up to some level of difficulty. And when it becomes harder, so we have this incremental training method that can help solve a bit harder problem. Again, there is also, there's a level where we cannot solve anymore, because theoretically, the problem we are trying to solve is very hard. And so we are still working in this direction. And so what I presented just before is the case where we assume that we have the initial predicates. But in practice, you may have some sensors like a camera, and you would like to extract this relational representation directly from this high-dimensional input. And so we are interested now to try to learn this symbolic or relational representation directly from images. And then if you can do that, we can plug that to our DLM method, and everything should work well. Another direction that we are interested in is to try, in fact, to use another formal language. So in fact, now that we have done this kind of work, my conclusion is that the first order logic is a too flexible language. And so it's very hard, in fact, to learn using this kind of language. And especially in reinforced learning, we are in fact trying to solve planning problems. And so trying to use a formal language that's more constrained to the task we want to solve would probably make the whole problem simpler. And so we are planning to do the same kind of work, but using a planning language as a way to describe the policy. Okay, so this is basically what I wanted to share with you today. So there were already some questions, but I can take some other questions if you have any. And I think I was over time as well, no?
You were a little bit, but not to worry. Thank you for your presentation. It's definitely a very hot topic. I know that because I'm just at the university and I have students coming who everyone wants to do interpretable ML in one way or another. So yeah, thanks for showing up on a short notice. Does anyone have questions?
Yes, I have one. Thank you very much for the talk. So as I see it, you have at least 3 dimensions of complexity in this approach. The first one is the amount of objects you have to deal with, number of instantiations of the formulas you learn. The second complexity dimension is the complexity of predicates, so the arity of predicates, for example. So as I see, in your environments, you used up to binary, up to 2 arguments, right? So all the domains require the binary predicates, but probably not ternary or predicates of bigger arity. And the third dimension is, well, but not the last one, of course, is how many steps of learning you need to learn these formulas. So how many rounds of interaction with the environment you need to learn the formula. So what kind of dimension is the most complex in your view, so in your experiments, in your experience?
Yeah. So for the number of objects. So of course, it depends on the task, but usually, so especially for block squares, for example, you could focus the training on instances with a small number of objects, and then learn from that. And the hope is that, yeah, if you learn the first order logic program, if it works on smaller instances, you hope that that it will generalize automatically on more number of objects. So I think a number of objects usually is not too big, is not too much an issue. Regarding the arity of the predicates, again, I think that this. So of course here we mostly use the binary predicates to describe our problem, but usually that's the case. In fact. So when it's quite rare that you need a much higher arity to describe your state or your observation. So, but actually in our architecture, when we train the model, we use a higher arity. So this is the example here, where although the initial predicates are only binary, so we allow to create, to invent predicates that are ternary. So that allows more expressivity in the logic program that we are going to learn at the end. But you are correct that all those points that you cited have an impact in terms of computational complexity and memory consumption. For example, the number of objects can have impact on the memory consumption, and so you at some point you will not have enough memory to just to represent the whole instance that you want to solve. I mean, if you have an instance where you have hundreds of objects, of course it's going to be hard to store everything in memory. And the issue with this approach is that everything is represented as tensors. So probably there's some work to be done to try to use other kind of representations to store the evaluation of predicates. Because here basically we are so it's not going to scale very well in terms of number of objects and also of the arity as well. So I think I answered over all the points. I don't know if I forgot one point.
Yeah, I also mentioned the number of rounds of interaction with the environment, but probably it's
okay. Yeah, so here it's like any deep reinforcement learning method. It requires a lot of 20 steps. So I don't have the numbers anymore because we did that. We finished this kind of work some time ago, and so I will have to double check in the paper. But I mean, computationally, it's quite costly in when you train the model.
Okay, thank you very much. Another interesting point, if I have some time, well, probably it's more a discussion right now, but well, interesting that if you allow predicates of bigger arity, probably your formulas become shorter and more readable. So this has direct relationship to interpretability if you read it broadly. Can it be the case that if you increase the arity of predicates, your formulas become more readable?
I'm not sure, because as a human, I think for me it's much easier to understand binary predicates or binary predicates. So it's more rare that you use a higher arity to describe. I don't know if you have some examples, but what can make the logic formula more legible would be to move to second order logic, for example. And so here you can make the program much shorter and more legible, but it also made the search for this kind of program even more complex.
And did you compare your model to black box models, deep RL black box models?
So not directly. So we compared with NLM, which is the main black box model we compare to. So for some of the tasks, yeah, I think we run also with some more standard deep reinforcement learning method. But the problem with this kind of technique is that they don't scale, or they are not independent of the number of objects. And so if your instance have a different number of objects, you cannot apply the standard deep reinforcement learning method anymore.
I mean, it would be in general interesting to know how other models, black box models, solve this kind of environments. So are they good at them or not, etc.
Yeah. So but the problem is the model you are going to train with deep reinforcement learning, with the standard deep reinforcement learning model, is that you have to choose the number of, or you could also, apply some kind of recurrent, maybe use a recurrent neural network to make sure that it's independent of the number of objects. But otherwise, the standard deep reinforcement learning method will not work well if the number of objects can change all the time.
This does raise an important point that like here we are looking at a different formulation of an environment, right? So our environment, our observations are provided not as vectors, but as the sets of predicates. And so we don't really have a direct comparison of interpretable of logic versus like standard deep reinforcement learning. And it would be great to have an interpretable reinforcement learning framework that I could just plug into any RL environment without all this predicate engineering, where the predicate engineering is really doing a lot of work for me.
Mm-hmm. Yeah, so that's the direction. One direction we are interested in is to try to learn directly this kind of relational representation.
Yeah,
I suspect this like representation part might be actually the harder part, right?
Yes. But we have some ideas here. But there are only in fact some related work like object-centric deep reinforcement, where they try to detect all the objects in the image, and from that you can then know their positions, and you can extract the relations between the objects. And so that's the first step to build this kind of symbolic representations.
Right. Yeah. Thank you. Anyone else have questions?
Yeah, I have a quick question just to see if I understand things correctly. Initially, I confused interpretable with understandable RL, and I think I might be misinterpreting things like that. So a human could interpret this, but it will grow very complex really soon, right? If your problems grow, then it still wouldn't help to actually understand what is going on, because the predicates will run into the thousands, and it would take years to understand what's happening. do you have a goal, an underlying goal to make things understandable as well, or are you just focusing on the interpretable part and then needing other ways to actually understand what is going on? Can you say something about that?
Yeah. So I mean, the meaning of all those words are not really well defined. In fact, so what I mean by interpretable is so here it just means that it's a logic formula. So you are correct that to say that if this logic formula is very long, of course a human will have a hard time to understand it. But I think the way to answer this point is that if when you have a logic formula, in fact there are many tools that can be used to verify the logic formula. So the people have worked on this in verification, for example, and so you can also use the reasoning to all the reasoning tools to, for example, to check that if you have a first order logic program, you can check if it can lead to some state that has bad properties. And so this can be done automatically by if you have a first order logic program, just by inference. Okay, and so even if it's hard to understand, by reading the logic formula by a human, I think it's this kind of interpretable solution is still better than having a deep neural network, because in deep neural network, for now, right now we don't have any tools to verify this neural network has good properties. Like, and so there are many people working in this direction to try to build these kind of tools for deep learning, but currently there's none. So and so so even if it's very long, I think if it's a logic formula, it has a nice property of it can be understood using other tools to analyze this logic formula.
And if you mentioned in future work you'd like to, as mentioned here, exploit planning languages, other languages, then would you lose the tools that are available now for validation, or are you looking into languages that have those tools as well?
Yeah, so I'm not an expert here in those planning languages, but I guess people have worked on this framework, and they have developed. As soon as you have some kind of formal language, it's much easier to analyze this kind of solution written in this language than a deep learning neural network.
Mm-hmm. Oh, very interesting. Thank you.
Another point to mention here is that you probably might know about the situational calculus, which is a powerful formalism for description of planning problems, well, for describing action domains. And there, the point is that people are developing the description of environments, the initial world, and the actions possible, the effects manually. So, and here it seems like you can provide a solution which does this fully automatically, right? And this could be a very interesting combination and update to situation calculus from my point of view.
Mm-hmm. So actually, there already works in this kind of direction. So this is so there are some colleagues who have tried already to combine this kind of planning language and deep reinforcement learning. So there are already some initial work in this direction.